As a chemistry teacher, I often need to teach my students about microscopic mechanism of chemical reaction in class. But this mechanism is very abstract and difficult for students to understand and have a profound impact on. Therefore, based on my job requirement and the skills I learned in this mathematical course, I conducted a research project with the title Visualization Design of Microchemical Reaction Processes based on Matlab GUI. First, let me introduce the abstract of this study. To provide a more vivid demonstration of molecular collisions and facilitate learners in establishing intuitive understanding, this study leveraged advanced mathematical tools and programming capabilities, notably Matlab, to develop and design a kinetic simulation program that visualized the collision process of A and BC triatomic elementary chemical reaction based on the COSIL classical trajectory method. By employing MATLAB's robust computational engine and its graphical user interface technology, we are able to extract detailed kinetic information during the collision process and create a dynamic and interactive visualization. The program, which is deeply rooted in mathematical principles, showcases the diatomic molecular collision process and its outcome through animations. Furthermore, through MATLAB's intuitive GUI, users can engage in real-time human-computer interaction, observing the evolution of atomic and molecular state involved in the collision from multiple perspectives over time, all while leveraging the powerful numerical and visualization capabilities of MATLAB. The typical reaction is used as an illustrative example to demonstrate the program's operational result. My research background includes 3 points as below. First, chemical reaction kinetics reveals the microscopic mechanism of chemical reaction. By mastering the reaction pathway, students can gain a deeper understanding of the reaction mechanism and process, thereby enhancing their comprehension of reaction and laying a solid theoretical foundation. Second, microscopic reaction processes are highly abstract, making it difficult for traditional teaching methods to present them intuitively. With the help of computer simulation and animation technology, complex chemical reaction can be visualized. The last one, this study aimed to solve the challenge of visualizing microchemical reaction process through MATLAB GUI technology, helping students learn better. Now, I will report my research method. First, application of classical trajectory approximation method. Integrating MATLAB GUI with Fortran numerical computation simulating molecular collision process using classical orbital approximation. Second, checking the trajectory of atomic nuclei by solving the Hamilton equations. Third, setting collision conditions with random numbers and propagating trajectories using numerical integration method. Fourth, the Fortran program is responsible for underlying numerical calculations, ensuring the accuracy of the simulation. Last one, the MATLAB GUI provides an intuitive user interface, facilitating real-time interaction and operation. To implement this visual teaching tool, we first need to build a user interface. The main interface includes functional areas such as state loading, parameter input, and animation control. It supports adjusting collision parameters, selecting viewpoints, and controlling the playback of animations. This is the code to build user interface. After the user interface is completed, we need to provide the trajectory file, which needs to be calculated using a quantum chemistry software function. The calculation principle is performed as below. Typical reaction is used as an illustrative example to demonstrate the program's operational result. Chemical reactions, when examined the stereoscopic level of molecules and atoms, can be conceptualized as a series of interactions, where reactant molecules with specific quantum states collide, leading to atomic rearrangement and formation of new product molecule in distinct quantum state. Throughout these collisions, the nuclear configurations of the reaction system are in the state of constant flux. Boyne-Oppenheimer approximation. The interactions during the collision phase of elementary reaction encompass interaction between nuclei, between electrons and the nuclei. To streamline computational process, the nuclear adiabatic approximation, also known as Boyne-Oppenheimer approximation, is often deployed. This approximation allows for the separation of electronic and nuclear motion, thereby introducing the concept of potential energy service. On this PS, formed by the electronic potential field, the motion of atomic nuclei is governed by classical mechanics, specifically Hamilton's equation. Solving Hamilton's equations. By solving Hamilton's equation, we can check the evolution of the generalized coordinates and momenta, the atomic nuclei over time, which are referred to as trajectories. This analysis enables us to determine whether recombination of atoms has occurred, whether a chemical reaction has taken place, and whether they have been changed in the energy state of atoms or molecules before and after the collision. The selection of initial conditions is typically facilitated by Monte Carlo's method, while the integration and propagation of trajectories are performed using the fourth-order Runge-Kutta with fourth-order extrapolation method. The initial and final state of each trajectory are described quantum mechanically, utilizing vibrational and rotational quantum numbers to characterize the internal energy states of the reactant and product. Based on the foundational principle of the classical trajectory method, numerous computational packages have been developed in Photon to calculate the dynamic properties of triatomic and polyatomic reaction systems. The computation of quasi-classical trajectories within the program involves several steps. First, inputting the various parameters, including collision energy, maximum impact parameter, collision shell radius, and initial vibrational and rotational quantum numbers of the reactant molecules. Second, utilizing random number to set collision parameters and initial spatial arrangement of the reactant molecule establishing the initial conditions for the trajectory. Third, integrating Hamilton's equation to propagate the trajectory. Fourth, analyzing each trajectory to ascertain the product and determine completion of all trajectory calculations. Fifth, conducting a statistical analysis of all calculated trajectories to derive information pertinent to chemical reaction upon completion. The trajectory program detailed spatial position and momentum of the three atoms at each time step of the reaction trajectory are obtained, with each trajectory's propagation information stored in a separate file. When we get the trajectory file, we can implement an animated demonstration of the trajectory by using Matlab GUI. Based on the trajectory file obtained from Fortune calculations, we can visualize it using Matlab GUI. During the visualization process, we need to load the trajectory file and transform the atomic position. The method for calculating position transformation is as below. Firstly, take the position of atom B as the coordinate origin. The coordinate matrix of each atom satisfies the following equations. The coordinates of the center of mass for the three atom system are determined by the following formula. This is the M-file code of animation. Now, after we build the M-file, we can simulation of the reaction in Matlab. Run M-file on the Matlab platform, and then click Run to display the main animation interface. Click the Load Date button, select the output check file calculated by the classical rail of the reaction system, and then click the Play button to observe the evolution of the atomic and molecular states over time during the reaction in the right display area. Using the output video files, a detailed analysis of the microscopic collision process of the chemical reaction can be performed, and different reaction mechanisms can also be reviewed. Now, I will demonstrate the running of this simulation program. First, open M-file and click the Run button. Load the trajectory file. Click the Play button. We can see the process of atomic collision on the right side. We can also pause or stop play while watching, and adjust the perspective.